All right, good morning, everyone. So welcome to the first talk of the day. Please give a hand for our speaker, Jessica Hamrick, who will be talking about games for science, creating interactive psychology experiments in Python with Pandas 3D.
Thank you. Just one moment. OK. Where is my mouse? There it is. OK. So yes, I'm a graduate student at UC Berkeley, and I'm going to be talking to you about some research that I've done with my colleague Peter Battaglia, who is a research scientist at MIT, and unfortunately couldn't be here at PyCon, but has been like a really integral part of this research. He was my mentor while I was an undergraduate at MIT, and actually I'll be talking about some experiments that he's done since I left MIT. So to start out with, first let's talk a little bit about games. So video games have become increasingly popular recently. As of May 2012, apparently, Angry Birds had been played a total of 200,000 years, with an average of 300 million minutes of playing time every single day, which is a pretty big number. To give you a sense of how big it is, 300 million minutes is approximately equal to 570 years. So that's 570 years of playing time just for Angry Birds every single day. That's a huge amount of human effort and time that's being invested into this one game. So wouldn't it be cool if we could leverage that popularity in order to do science? Like, we could do so much science if we had that much manpower. So that's the idea behind this talk, is creating fun games in order to do interesting science. And to give you an outline of what I'll be talking to you about, I'm first going to go over the research question that we're interested in. I'll then tell you what our hypothesis is that we think is going on. And then I'll tell you about the experiments that we've run in order to test this hypothesis and the tools that we used to make those experiments. And the tools that we do use to make these experiments, they're not too difficult to use, so I think anyone in this room would be able to pick them up fairly easily. We have some demo code that's online. You can go and look at it. As I'm going through the talk, if this is interesting to you, you could probably do something pretty similar if you wanted. OK, so first of all, what's the question that we're interested in? So we're fundamentally interested in how people reason about the world, and in particular, how people reason about the physical world. So from the time that you get up in the morning until you go into work, you've already interacted with the physical world in ways that no computer can even begin to rival. So you've gotten up, you made breakfast, you got dressed, you put things into your bag, you drove to work. A computer can't do any of those things. Well, I guess maybe they can drive now with the Google self-driving car, but a computer definitely can't do all of those things, and definitely can't do it as fluidly and as flexibly as people can. And so you might think, well, maybe that's just because we have lots of experience with the world. You get up and make breakfast every morning, so you just, it's easy because you do it every day. But I think that our ability to reason about physics is much more flexible and much more powerful than that. And to try to convince you of that, I could show you a table with some blocks on it. You've probably never seen this table before, or this particular configuration of blocks. Yet, if I told you to imagine that maybe there's some kids running around and they bump into the table, some blocks fall off, you probably have a pretty strong idea of which color block is more likely to fall off. So just shout out what you think. Do you think it's red or yellow is more likely to fall off? Red. OK, right. How about this one? Right. OK, this one? All right, red. This one? Maybe yellow? How about this one? Yellow. OK. This one? Red. Right. So just from these few scenes, you've never seen these before, yet you all have a pretty strong opinion of what might happen. And in general, you agree with each other. The level of agreement can vary from scene to scene, but it seems like there's something pretty systematic and some really powerful, flexible reasoning going on. And so this is exactly the thing that we're interested in, is how is it that we can reason about these types of scenes? I think that's really interesting. So that's the question, is how people reason about the physical world. So then now I'm going to tell you about what our hypothesis is that's going on. So the field that I'm in is called computational cognitive science. And in computational cognitive science, we view the brain as a computer, and we're interested in how the brain generates thought and behavior. And in particular, in computational cognitive science, we are interested in how the brain's software works, so how the software produces behavior. Our colleagues in computational neuroscience are interested in the hardware, and that's more like the individual neurons. And so our scientific approach is to come up with theories of how the mind's software produces thought and behavior, and then instantiate those theories in a computer model. So that might be a robot or an artificial intelligence, but it's something that can produce behavior just like people can produce behavior. And then we can compare the behavior that the model produces with the behavior that people produce in order to test our theories and fine-tune them and come to a better understanding of how people think. So how do we create a model of how people reason about physics? Well, luckily for us, there's already lots of software that does physics. So for example, the physics engine in a video game like Angry Birds. And moreover, if we take a look at physics games, this seems to offer us a really nice platform for studying how people reason about physics, because it requires the same types of reasoning faculties that you need to interact with the everyday world. So this is sort of where we started, what we were thinking about, and we took this pretty far. And what we hypothesize is that you actually have a physics engine in your head. So you look at a scene, you form a representation of it in your mind, and then your mind actually performs a simulation of simulating forward the future to get an outcome. You can then use that outcome to make a decision about something in the world. And there's two components to this hypothesis. The first is that this physics engine is approximate, meaning that the simulations it runs aren't exact. And the second is that it's probabilistic, meaning that if you run the same simulation twice, you might get a slightly different answer. And the reason for these two components is because the world has uncertainty in it. So for example, I could show you this picture of these rocks, which you might think maybe was taken just at the moment they're about to fall, or perhaps is even photoshopped. But actually, it's neither of those. This is a real photo that's taken of real stable structures. This is a sport. It's called rock balancing, and the goal is to build these crazy structures that look like they're going to fall down. It's pretty cool. But if they're actually stable, but we all have this impression that this must be about to fall down, our model needs to be able to account for that. And so we think that it would take so many coincidences for the structure to actually be stable that our mind says, that a combination of coincidences is so unlikely that I'm going to say that it's probably going to be unstable, rather than assuming all these coincidences are going to happen. And so that's sort of the important approximate and probabilistic component that can handle these types of uncertain situations. And we can extend it beyond rock balancing to maybe a tower of blocks in a game of Jenga, or to a 3D model in a physical simulation, like the type that we run in our experiments. So this is an actual stimulus from our experiments that is actually stable, but it looks very unstable. All of our participants always say that it's unstable. And our model also says that it's unstable because it has this approximate and probabilistic component. So the reason why we think a physics engine is a good idea is the same reason why it's a good idea in games and graphics. So first of all, it's effective. Like, it can produce simulations that are sufficiently realistic to fool you into thinking that it's maybe not a real scenario, but a good depiction of a real scenario. It's efficient, so it's made to run in real time. And similarly, the physics engine in your head has to be able to run in real time. You can't just sit around all day waiting for your simulations to complete before you make a judgment about some scene. And then finally, and I think that this is the most important one, is that it has to be general purpose. So the physics engine in your head has to be able to apply to many different types of situations, because the last thing that you'd want is to encounter a situation that you didn't have experience with and not know how to act. So apparently this is a sign somewhere in the United States. If you look closely, you'll see that, I guess it's a little dark, sorry, but this is not a rock, it's a cow. So apparently somewhere in the United States there's a danger of cows falling off of cliffs onto your car. Hopefully none of you have been in this situation. But if you were in this situation, I am pretty confident that you'd be able to do something reasonable and deal with this scenario, despite the fact that you've never been in that scenario before. So this ability to reason about things that we have never experienced is really, really important. So that's sort of the motivation behind why we think this physics engine idea is a good idea. OK, so that's our hypothesis, the physics engine in your head. So now, finally, we can get to the actual experiments that we ran. So the way that we are going to test this is by taking the tools that people have used to make video games and to actually use them both as our theories, so we can use the physics engines from these games as a theory of how people reason about physics, and we can use it to create these really rich and engaging experiments. So our general research pipeline goes like this. First, we can create a computational model, and we do that using a video game physics engine, for example, Bullet. Then we can generate stimuli to test our model and also people using a 3D modeling program like Blender. And then we can run experiments using a video game framework like Panda 3D. And all three of these tools that I mentioned are open source. They all have Python bindings. So they fit really nicely together. They work really well together. And it fits into the larger picture of Python and science as well, because we can do all of our data analysis using NumPy, SciPy, et cetera. And then we have this really nice, powerful framework for doing research, all the way from the level of creating the model to running the experiments to doing the data analysis. So for the rest of the talk, I'm just going to focus on how we did the experiments, so I'm not going to talk more about the model or the results. But if you're interested, we have a project page. We have a journal article published in PNAS and 2 popular science articles. If you want to go read them and read more about the details, you can go do that. And these slides will be online, so you can look at them at your leisure. OK. So first, I'm going to show you one of the simpler experiments that we ran to give you a sense of the types of things that we're testing. So in this experiment, we had people look at these towers of blocks. And again, this is a little dark, so it's hard to see. But so you have these towers of blocks, and they all fall down. And people have to decide what direction they think the tower will fall in. And they do that by moving this white line around the table in order to point in the direction that they think it's going to fall. And I'll show you a short video of what this looks like. So here you see the camera spinning around the tower, and the video is not playing. Well, that's unfortunate. Luckily, I have a demo. I'll show that instead. So, OK, camera spins around the tower. And now the line appears, and I can move it to point in the direction that I think it will fall. I think it's going to fall there or so. And so that's the general idea. It just repeats from there on. But this is, traditional psychology experiments, usually you will just press a button to say, yes, I think it's going to fall, or no, I think it's not going to fall, or give a rating on a scale from 1 to 10. This is much more engaging than that, because you can actually make a judgment in the 3-dimensional world in real time. So it feels like you're actually making a judgment about a real scene, as opposed to something that's just on your computer. So OK, how do we do that? So the sort of general flow of how this works is we first create graphics models to depict the objects in our scene, so that's the blocks. And then we actually have to render those models, and we do that using a rendering engine. We then can add physical dynamics using a physics engine. And then we link the graphics and the physics together so that when physics is simulated, the graphics will move along with it, and so it looks like a realistic simulation. So I'm not going to go into the specifics of the code here. I'm just going to go over a conceptual overview of these steps. But I have code online for the demo that I'm going to be showing you, in addition to the other demos. And so you can go look at that if you're interested. Also, Panda 3D has a really good Hello World tutorial that's good to get started with if you're interested in that. OK. So step 1 is to create a graphics model. And you typically do this in a separate program, a separate 3D modeling program like Blender. Some of you, so you might have heard of Blender. More of you may have heard of Maya, for example. But I like Blender because it's open source and it's Python scriptable. And so what you end up seeing here is on the bottom these are different views of the geometry. The jargon term is like mesh. So here is a view from the top down. These are two different side views. This is a camera perspective view of what the preview will look like. Over here, we have the texture that we're going to apply to the mesh. And then here is the final rendered preview of what our graphics object actually looks like. But this is just a static rendering. So what we want is to render it in real time. So what we're going to do is pull it into a graphics engine, rendering engine, like Panda 3D. And Panda 3D is written in C++, but it also has Python bindings, so you can do everything in Python with it. So the way that Panda 3D decides what to render is it has this thing called a scene graph. And at the root of the scene graph is a special object called render. This is a hierarchy of objects called node paths. And the node paths basically point to more specialized objects, like models or lights or a camera. They're the way that you interface with those objects. So at the root, we have render. Everything under render will get rendered, hence why it's called render. And so we can load in our model. So if we had saved the previous model that I showed you, for example, as woodblock.egg, and egg is just the extension that Panda 3D uses for its models. So we load that in. We create a node path called block graphics to point at that so we can interface with it. And then we add block graphics to the scene graph. So now if we were to run Panda 3D and look at it, we would see a block. It's not very interesting at this point. It's just a block in the middle of the screen. But it is being rendered in real time, which is what we want. So we can make it more interesting by adding in physics. So to do that, we are going to use a physics engine called Bullet, which is also written in C++, but also has Python bindings. And more importantly, it's actually included in Panda 3D. So it has built-in support for interfacing between Panda 3D and Bullet objects the same way you'd interface with any other Panda 3D object like the model. So the way that we render simulate physics is by creating an object called a bullet world. And this keeps track of all of the physical objects. And it computes physics. So if you do one time step worth of physics, it'll figure out what the next position of all the objects needs to be. If any of them are detected as colliding, it will figure out how they bounce off of each other, et cetera. And so the way that we represent physics objects are through two components. The first is a shape, or a collision geometry. And that basically specifies how the algorithm that computes collisions works. So depending on what the object is that you're trying to simulate, you might want to use a sphere or a box or maybe a cone. All of these are collision shape primitives that you'd want to use here. And the other thing is the body, which actually specifies the dynamics themselves. So this is stuff like mass, the center of mass, friction. So you combine those two, and you get a full physics object. So we are going to create our physics world. And then we can create a shape. Here we'll use a box shape because we're doing blocks. And then we create a body. We set the shape as a child of the body. And then we add the body to the world. So now we should be able to simulate physics. And in fact, hopefully this video will work this time. So this, it might be hard to see in the back. But this block now has a red outline around it. This is actually a special debug mode that Panda 3D has, where it'll render like a skeleton or a wireframe of the physical objects, which is really useful in telling where they are or what size they are. And this blue line sticking up is just the z-axis. There's also a green line, which you probably can't see, which is either the x or the y-axis. So if we run this, what we'll see is the physics object falls down, but the graphics object does not. I can play that one more time because it went a little fast. So this isn't exactly what we wanted, though we actually probably could have predicted it, because if we take a look back at our graph again, these two parts are not connected. So like Panda 3D doesn't actually know that graphics and physics should be linked together, so we have to explicitly tell it. Because Bullet's included with Panda 3D, we can create a node path and point it at the physics object. And then if we set the physics object to be a parent of the graphics, now this is really the powerful part of the scene graph, is because it's a parent of the graphics, when we move it around, the graphics will also move. And you can do this even with like empty node paths. So if you had a whole tower of blocks, you could have a node path just for the tower, and then individual node paths for each of the blocks. If you move around the big node path for the whole tower, it will move around all of the blocks as well. So if we set it up like this, now when the physics moves because of the physical simulation, graphics will also move. If we take a look at what this looks like, we now see that the block falls, both physics and graphics, which is what we wanted. So this is a pretty simple example. It's not nearly as interesting as the demo that I showed you, where you judge the direction that it's going to fall. But this is sort of like the basics that you need in order to do this. Once you are able to do this with the physics and the graphics, you can do the rest fairly straightforwardly. So I'm going to show you 2 more demos of experiments that we've done. So this one is, I tried to come up with a short, cute name for it, and I couldn't. So it's glue blocks together to make the tower stable. And so that's basically the idea, is you can create attachments between blocks. So here the green block and the purple block are attached because it has this like white glue stuff in between. And you want to try to make as few attachments as possible in order to make the tower stable. And then, for this experiment, we actually added in the idea of having a score. So you get points for every block that stays standing, and you lose points for every block that falls down. You also lose points for each attachment. So it really motivates people to try to make as few attachments as possible. And so this is really, a much more engaging, interesting, goal-oriented experiment than the previous one. I think it's a lot more fun as well. I'll try the video. Hopefully it will work. We'll see. So that's what it looks like without any attachments. It just falls, obviously. We can make some attachments that might not necessarily work, but you see the objects there are attached. And we can make attachments that actually make the tower entirely stable. So here we run physics, and it doesn't fall down. So that's the idea behind this experiment. The next experiment is, in my opinion, the most fun. So you might notice this looks kind of like the tables that I showed you at the beginning with the red and yellow blocks on them. So we actually did run that experiment. This is the next version of it. So instead of saying that the tower or the table will be bumped, we're saying that you have to bump the table in order to knock off the yellow blocks, but not the red blocks. So you get points for every yellow block that falls off, and you lose points for every red block that falls off. And you get to choose the direction and magnitude of the arrow to specify where to bump the table and how hard to bump the table. And so this is really fun. Jokingly, we can call it Angry Blocks 3D because it's not exactly like Angry Birds. In that case, you have to throw a projectile. In this case, you are bumping a table, but you're still trying to knock over this structure. And so it's really fun to do. I often, when I'm talking about it, rather than saying like I'm doing this experiment or whatever terminology I'd normally use, I'll say like I'm actually playing it. So I'll show you a video of what it looks like. So there's the camera spinning around it. Yeah, it's these videos. I don't know. I also have a demo of this though. OK, so there's the camera spinning around. Here's the arrow. I can change the size, make it smaller, make it bigger. So I'm going to bump it here. And most of the yellow blocks fell off, which is good. All right, do this one. You can also change the viewpoint if you need a better view. And so on and so forth. I really like this one. It's so much fun to do. Like I feel like I could do it all day. And actually, so Peter, my colleague, ran this experiment on people at MIT, and he said that people reported to him that they'd be willing to pay to do this. Whereas like normally we pay them money to come in and do the experiment, right? Because normally like psychology experiments, they needed an incentive to come do it. But they'd be willing to pay for this. That's awesome. So that's the idea. Those are all the experiments I have time to show you today. If you're interested in doing any of them personally, you can come talk to me afterwards. I have the demos on my computer, so you can run them. So just to wrap up, we asked the question of how people reason about the physical world. And our hypothesis was that you have this physics engine in your head. And I showed you some experiments that we built using these tools, Blender, Panda 3D, and Bullet, that are really fun and engaging and really are a good way of testing this hypothesis. And I didn't talk very much about the model, but we use these same tools to make the model, and we find that this model is a pretty good account of how people reason in these situations. So, coming back to the beginning a little bit, I showed you this quote about Angry Birds, and I asked you to think about, how much science we could do if we had that type of popularity. And I think that with these types of engaging experiments, it doesn't seem that implausible that we could do something that's pretty popular, like Angry Birds. Maybe not quite at that scale, but if people are willing to pay for the last one, if we got it on an iPad or something, I think we could really scale this up and get a lot of data. And that's a really exciting possibility to me. So I just wanted to thank the people who've been involved with this project. Josh Tenenbaum, who is my advisor while I was at MIT, and who was a co-author on the paper that we published about this. Tom Griffiths, who's now my advisor at Berkeley. The labs that I was in, both at MIT and now at Berkeley. And of course, all of the tools that made this research possible. Python itself, the 3 tools that I've been talking about today, Panda 3D, Blender, and Bullet. IPython, NumPy, and the rest of the SciPy stack. And these slides actually were created using the IPython notebook. And converted to reveal.js. So really, Python has been an integral part of this whole research from the very beginning all the way to presenting it at the end. Again, here are some links if you're interested in learning more. Thanks. OK.
Okay, so now we will be doing Q&A. If you have any questions, please line up at the microphone in the center there. Thank you.
Go ahead.
Hi, thanks for the interesting talk. I'm just wondering about what could be the possible cost for the engagement. What makes it so addictive to simulate the physics engine in our head? Do you have any thoughts about that?
You mean like what's in the brain that lets us do that?
No.
Or?
So why is Angry Birds so popular? Why does it make it so addictive? What is it?
I see. That's a good question. I don't have like a super great answer to that. I think probably partially because it's challenging, and partially because it requires us to use machinery that we don't normally have to use, but that we are good at using when we do use it. But I think that's like an open research question, so it's a good question. Thanks. Yeah.
Hey, thanks for the talk. I was just wondering about the capabilities of Bullet. For example, if you were to simulate really small scale stuff or really large scale stuff, the physics would be very different, right? So
yeah.
Do you know how capable it is?
So Bullet won't do super large scale stuff, won't do gravitational effects beyond just rigid body gravity. Super small stuff, I don't think you mean necessarily at the level of atoms and stuff, but no, it can't do that. In general, if you get too small or too large, it sometimes runs into instability issues. So it requires a little bit of tweaking to get that working quite right. But it's pretty robust for things that are the size of people of that magnitude. It also can do things like cloth simulation, which we haven't done anything with yet, but it has other capabilities that are really interesting too.
Hi. First of all, I love the enthusiasm with which you play with your experiments. That's amazing. A brief academic sidetrack. I was working with probabilistic models for educational data about a year ago, and I stumbled across your MIT group's research, where causality and Bayesian inferences played a huge role. Do you work with that stuff in this particular physics engine?
Yep.
And if so, you did mention some of it in the beginning. So how would you structure your a brief? Obviously, at this point in time.
Great question. So the way that the physics engine works in terms of making predictions about stuff is it's not really Bayesian. You run some probabilistic samples, and then you can like aggregate those samples. You just take the mean of them. But I've been doing some work in looking at how people actually can infer physical properties from watching like these types of simulations. So like if some of the blocks were heavier than others and it caused the tower to fall in a different way, like can people make those types of inferences? And that requires using a Bayesian model. That's work in progress, but yeah, definitely that's the type of modeling that we're doing here. It's really cool.
Right, and so what actually brought me to ask you about this is with every successive, I mean, it's an obvious thing, with every successive experiment you see, the more data you collect, there's belief updation, and whether this particular one is, okay, so you're saying this is not a graph structured inference in particular, but there's other research here.
Well, for stuff with like inferring mass, we can definitely do things about belief updating. In this particular, these experiments that I showed you here wouldn't require anything about belief updates. But,
Okay.
But I'd be happy to talk to you more about it later.
Yeah, sure.
Yeah.
Thank you.
Oh, one more question. Yeah.
I had more questions about BulletWorks and how the capacities of that. So, like, can it do stochastic simulations or like compressible objects or non-physical things like gravity going up? And have you played around with those in experiments?
Good questions. So it I think it can do deformable objects, but I'm not entirely sure. We haven't done anything with that yet. In terms of probabilistic or stochastic simulations, Bullet itself cannot, but that's essentially like what we're building on top of Bullet to create our model. And then in terms of, I'm sorry, what was the last question that you asked?
Adding forces that are not present
Oh,
in the
right,
physical
yes.
world.
So yeah, actually you can set the gravity to be whatever you want. It's not, negative 9.8 by default. You have to just set that. So you could absolutely set it to be 9.8 instead of negative 9.8. And there's some really interesting experiments that people have been doing in terms of like having people reason about situations in which the gravity is like flipped upside down. It's not stuff I've done, but it's a really cool area of research. Yeah, thanks.
Awesome.
Okay, thank you.